Thank you very much. So what I'll be talking about is going to do a lot less with banking, but a lot more with what is happening in the world of data, right? So data landscape is definitely being disrupted. It's changing dramatically, and many very large organizations are finding themselves completely lost in terms of their ability to deal with this change. And a lot of that change has to do with data science. So we'll talk about that. We'll also talk about some case studies. I've chosen a couple of case studies on two extremes. One has to do with IoT and doing data science in very, very small organizations. The other goes all the way to the other extreme at a very large place like Barclays, and I'll summarize four case studies there, very short ones, just to give you an idea of the breadth of where this stuff is applicable. However, I think the biggest part of my emphasis is around just dealing with this change and the importance of a lot of things that we as data scientists almost never think about when it comes to where the data sits, how it's manipulated, what we can do with it, and where the real difficulties are. So if we start out and say, why should a big bank care about data? The story is simple. If you go back, 60, 100 years, the business was a lot smaller, it wasn't online, and a branch manager could know exactly what a customer wanted, what their situation was, who's getting a divorce, who's getting a college degree, who's moving, who wants to buy a house, who's in trouble financially. So a lot of the things that banks do today and actually pay billions of dollars in fines when they fail to do them, like KYC, as in know your customer, like assessing the credit risk correctly, like modeling the true risk, etc., used to be very trivial. Nowadays, they're extremely difficult because you have scale, and it's very hard for banks because they do have the data, but they don't have the access to it. And we'll talk about that as we go through the examples to achieve that customer intimacy. So in a grand vision of things, I'm not going to spend much time on the slide. All it says is, say a bank like Barclays, there's literally millions of interactions per day with customers. If somebody calls the call center, they go on the web, they visit the mobile app, they do a bunch of things. And each of those interactions is an opportunity to either learn something about the customer or act, i.e. maybe cross-sell, upsell, educate, communicate, etc. Today, no bank actually does this. So I want you to ask yourself why. Why is it so hard for these places? And we'll talk about that. Now, in an overall framework, what matters in the age of analytics is, can you exploit all the data that's available? And we're going to come back to these questions at the end. Can you spread the analytics everywhere in the organization? And can you drive significant value from those analytics? So those three areas are the areas that we're going to come back to at the end and try to answer these questions. Where are we today? Now, along this journey, I'm going to start talking about something called data fusion. So in the introduction, and by the way, background-wise, I'm not a banker. I only moved into Barclays 2.5 years ago. So my background is in technology, lots of technology companies, my own, and bigger companies like Microsoft and Yahoo and others. But we started on a project that was a bit challenging for the bank. It was in cybersecurity, right? And we have a real amazing Chief Information Security Officer. His name is Troels Erting, and he used to run Europol, right? Basically the police in the Eurozone. And he was used to very expensive hardware, analysis, all that kind of stuff. So he came to the bank and he said, can't we get all this data from all over the place in order to put it in one place to analyze it? Call that the data fusion cell, where we can detect events as they happen. So be they trade activities, be they application logs that are unusual, an application that's accessing data in a new way, A lot of the threats inside a bank come from insiders, right? An employee who's trying to do something wrong that's going to wind up costing the bank a lot. And of course, all the external data from social networks, credit card transactions, all sorts of other stuff that we collect from point of sales and so forth. That sounded crazy, but that drove this sort of architecture where we bring everything onto big data, because that's the only affordable approach to do it. And the goal was to satisfy cybersecurity. Now, I'm going to come back to this. That same pattern suddenly became the useful pattern for things like compliance or trade monitoring, for fraud detection, for financial crime, for marketing, for operations, for risk, and so forth. And I'll give you examples of these. Now, this is critical to think about. What do you do with this? And that's what most of the talk is going to be. A, you need a big data infrastructure to do this. You cannot do it on the normal database infrastructure. But then a whole bunch of problems show up when you do something like this. But if you do it right, there's a whole bunch of applications from the same pattern. And that's going to be the big theme here. All right, you all know big data. It's basically platforms that can deal with mix of data between structured, unstructured, semi-structured, all put together. Typically breaks normal databases. And it leads to messy situations, and a lot of people here call themselves data scientists. And I think I picked up this definition of data scientist about a year and a half ago in a conference. It's someone who knows a lot more about software engineering than statisticians, and knows a lot more about statistics than software engineers. Now, that combination is hard. And that's why finding true data scientists is difficult, and that's why they are the highest paid technical positions out there. Cybersecurity comes close, by the way. So first of all, is there a lot of unstructured data out there? What's the big fuss? And I don't like to use some of the statistics you hear from companies like Google and others. You know, humanity generated more data in the last 2 months than they did since the beginning of history. True, if you count as data things like voice over IP, which is communications, or of course, the largest source of data on the internet is what nowadays? Anybody want to guess? Netflix, yeah, basically video streaming in general. YouTube is still also up there. So, if you count all of that as data, this is true, but that's not really data, right? This is basically just streaming and moving data. What I count as data is, what are enterprises really spending to store and persist that data? And the story there is still pretty interesting. The majority of that data is unstructured. And these are real data stores with real money spent by enterprises. This is a report by IDC. And it essentially says that in 2015, end of 2015, we were sitting at about 60,000 petabytes or 60 exabytes of this stuff. So it's a lot, but it's not that much, right? However, the thing to note is the majority of it is unstructured. People talk about the 3 V's. I'm not going to spend any time on them. I like to talk about the 4 V's, right? So the 3 V's are volume, velocity, and variety. Volume is easy to deal with. That's really big size. Velocity is how fast the data is coming. It gets pretty tricky here, and we'll talk about that some. Variety is the hardest, which is when the data is unstructured and is a mix of different types. What do you do? So here's a record of, a highly structured record from information we know about a customer in a bank, right? So we certainly know their gender, age, address, where they work, how much money they have, and a bunch of other things, what products did they subscribe to, etc. Now, most banks, by the way, don't know this in one place. So it's a challenge to just have the one 360 view of the customer. But let's assume you had it. And you might have this for millions of customers. I'm going to show you in a second that any database today, one like this, maybe people in this room, can be turned into a big data set in no time with a lot of free data sources, right? So you've got LinkedIn, you've got to pull in all sorts of information, both on the professional graph as well as on the individual, their job description, all that. Google will get you a lot of hits around this person, their hobbies, what they do, the place they live, all that stuff. Facebook, which gives you a lot of information about the social side of it. And even if you're like me and you don't have a lot of information about yourself on Facebook, it turns out, I have like a few thousand friends that most of them I don't know on Facebook. But it turns out that the likes of these friends tell a hell of a lot about me. And there's a whole talk I can give about deriving, for example, shopping preferences from Facebook data, where nobody typically goes to Facebook to shop. But you get it based on what your quote-unquote friends do. YouTube and Flickr, all sorts of videos, images, and so forth related to the individual. Data and metadata and all of that. Blogs, publications, articles, what have you. Now, everything I listed here is pretty much free data. And everything I listed here is pretty much augmentation you can do to any normal structured database. So in absolutely no time, you can take any database and turn it into a big database. Big in the sense that it has structured, unstructured, graphical data, all that good stuff. So the distinction between the two is fast disappearing. And that's essentially basically saying every company is becoming a big data company. We don't have time here to talk about data governance and sort of data architecture principles, but I wanted to summarize them here. I've listed a bunch of data management principles on the left, saying, you should really fuse data at the source, right, when it is created. You should standardize it. You should be careful about encryption. You should do all these things that sound very obvious. And on the right are the principles for data architecture, right? Data must have an owner. Data types must have a single definition. All that stuff. You read it. Sounds obvious. Does any of it sound controversial to you? Do you know of any organization that obeys any of these rules? This is the scary thing, right? I could tell you in banking, they don't. This is one of the sources of data mess, and we're going to talk about many sources of data mess here and what it means for us as data scientists. And we'll come back to that in the very end in a summary. So what should users of analytics in the real world do? A lot of you hear about the magic data lake, right? So load yourself a data lake, and everything will be fine, right? What does that mean? Well, here's an example. GE did it, 340 terabytes worth of data, 2,000 times faster, 10 times cheaper, all beautiful stuff. The real question now, and they achieved the first goal of analysis, is what happens to this data lake 2 weeks later, 2 months later, right? A year later. Who's defining the attributes? Who's dumping data? What happens when the data changes and the business changes? What's in that data lake, right? And what happens to this data lake is typical of every data lake I've seen. It very quickly turns into a toxic dump. What that means is it very quickly turns into not an asset, but a liability. Because it's sitting there, you don't dare delete it because God knows who's depending on it. But at the same time, who knows what the heck is in it, right? And by the way, this is not unique to banks. It happens in all industries. That mess of having data lakes, along with the original mess, and we'll come back to that mess in terms of application databases, the data warehouse, if it even exists, the data marts, the BI stuff, all of that. How do you, as a data scientist, get data out of this and make sense of it? Right? So here's the first question. Supposedly you know how to do magic with data. The real question is, when I tell you go get data, what data do you get? And what happens if you find 5,000 copies of the same data set, which you will in many large enterprises, right? If you have the column called, customer products, 5, and there's 6 of them, and they have different kinds of information. How do you know which is the right info and so forth? That's a challenge we'll come back to in a second. I borrowed this slide from a company called Waterline. They basically say grabbing data from a data lake is like shopping in a flea market. You pick up an item, you don't know where it came from. Is it the original item or is it a copy? Was it stolen? Is it legal entity or not? Let's say you don't want to grab it right now, you're going to come back to it tomorrow. Will you find it? But typically what happens in many organizations, including my own, is you get a lot of these, you load the data up in the data lake, lots of congratulations emails, and then now what, right? Now you have a data lake, and what happens next? And that's a pattern that's problematic. So, is this problem solvable? So I'm going to ask you guys, is this solvable or are we doomed? Data ponds, I got one answer. I don't know what that means. But maybe that's another talk. So I claim that a lot of you use this. One of the probably largest, most toxic data lakes, could be most toxic data lakes, but it is sustainable and it is very healthy. Anybody know what I'm referring to? Any guesses? Come on, I think you guys use it maybe 2 or 3 times a week at least. Huh? Wikipedia? Ooh, that's an interesting example. Although I'm not sure that's a great example. But there is one that's very inspirational to me. Amazon. Amazon sits on probably one of the world's largest, most toxic data lakes. It's not just their own data, it's data from vendors, data from other sources, all of that stuff. Yet you have a simple search box. You can refine the search. You click on an element and you actually find its right picture, its right description, and magically you have the right price on it and all that good stuff, right? So it works. And this data lake is being fed by all sorts of parties, all over the place, right? Now the trick to that, we'll come back to how do they do that. Now in reality, what do you do if you're a data scientist, you'd like to mine the data, and you end up spending all your time dealing with these headaches? Where is the data? Which table do I believe? How do I put these two things together? The IDs don't match up, right? And so on and so forth. Of course, you go to the engineers and the existential question is to Hadoop or not to Hadoop. Hadoop was built with a lot of thinking about MapReduce, yet nobody really uses MapReduce. The real economic drivers of Hadoop is not the technology, and I was involved at Yahoo when we launched it. It's really the cost of storage, right? So 20 to 50K per terabyte per year is a typical data warehouse appliance. 1K per year per terabyte is the typical cost of a Hadoop. That's economic driver number one, right? Of course, the Hadoop stack has been getting very interesting. Started simple, now it looks something like this. I used this slide 5 years ago. These are the ways you can actually query data. There's the relational world and the non-relational world, right? I looked it up about 3 years ago, it looked like this. I looked it up about a year ago, it looked like this. Now, this is only technology for querying the data, right? And of course, we can do the similar thing much deeper and much more confusing in Hadoop. So I said cost of storage is the big economic driver. What would be the second economic driver? Let's have a guess. Compute, good guess, but wrong. What? People? That's a good one. Oracle licenses. Actually, ETL. So ETL is extract, transform, and load. The new big data world says you don't do ETL, you do ELT. You extract, load, and transform, and then you stop. Now, this is revolutionary. This means you actually grab the data, and by the way, in a bank, we pay tens of millions a year for ETL software. It's the second biggest driver. The reason it's driving Hadoop is because on Hadoop, you do it pretty much for free, and guess what? You can also do it on unstructured data, which a lot of the ETL tools don't know how to deal with. Now, what's interesting about this ETL to ELT is it solves one of the biggest evils in enterprises. How does data get messy in the first place? In the highly structured relational database world? Very simple. App engineers like to build applications. Whenever they want to build an application, they create their own app database. What does that mean? Their own copy of the data, right? And then they basically, you get another 10 apps a year, maybe 100 in a few years. In a decade, you have thousands of apps running with definitely thousands of copies of the data, each with its own variations. And now you have a mess. Now when you tap into it and you say, I want to get that data, you get lost. Big data changes that in a big way, right? Because the second thing about this ELT is one of the biggest reasons why Hadoop gets criticized. People tell you it's a waste of processors, right? You've got a lot of storage, cheap storage, but the processors, you're wasting them. Turns out they're an asset, right? Because processors say, I can bring applications to data, I don't have to move the data anymore. That is huge, and that's a big change of one of the drivers. So I'm going to talk about a couple of case studies very quickly. I think I'm running out of time, so I want to shorten it because I want to spend a little bit of time on lessons learned. One of them, I actually borrowed from Joseph Sirosh because Sirosh at Microsoft. I love this example, right? The example, it's these cows that are hanging out and they're wearing these nice little pedometers. So why are the cows wearing pedometers? I love this example because it shows you that even the smallest businesses can become big data businesses, and I'll spend 2 minutes on it. So are the cows basically required to take 10,000 steps a day, like me? The answer is, farmers, they can do one of two things. They can either detect health issues, or they can improve cattle production by detecting when a cow is ready to be mated, basically. So, to do this, I don't know what's happening here. We have invisible font. It's a big economic driver of, I don't know why this thing is not displaying, guys. Okay, all it says is, if you move the detection rate, so in farms in Japan, detection rate is about, oh, there it is, showing up now. Wow, 55%. If you could increase that detection rate to 95%, you get a 67% increase from 40%, which is a big economic driver. That's about 70% increase in one of the biggest economic drivers for a farm. This Mac is taking its time now updating, so. All it says is increase. Okay, come on, come on, come on. Huh. All right, let's hope it doesn't misbehave on the next slide. All right. Okay, this is hard for a couple of reasons. One, it only occurs every 21 days, lasts for 12 to 18 hours, and occurs mostly at night, between the hours of 5 p.m. and 2 a.m. So the farmer is going to have to stay up all night watching to do it accurately. So how do you scale it? This is a picture of the actual data scientist in Japan, in Fujitsu, and the actual farmer in Japan that started it all. And the reason I like this example is I did my PhD in AI, artificial intelligence, at the University of Michigan in Ann Arbor, where there's a lot of farms around. So when I used to go to give public talks, people always thought I was talking about artificial insemination. And this example is AI finally meets AI. So this is the setup. This is the big data setup, right? The cows come into the shed. There's a router. It reads the information, of course, sends it to the Microsoft Cloud, Azure, and into the headquarters of the farmer, which is the kitchen table. And on that kitchen table, you actually get a record of, here's a normal cow. I don't know why it's doing that. And here's a cow that's going through estrus. This thing is adding animations of its own. So what this tells you actually is a very easy signal to detect when it starts, and that gives you a 16-hour warning that this cow is now ready, right? Now it gets better, even as amazing as this is. If you act slightly before, you get a probable female baby. Slightly after, you get a probable male, right? Now these are small businesses, right? And they're doing data science that's better than I've seen at some of the biggest organizations. By the way, oh man. It's either the Mac or I think it's this Captasia software. Should we terminate Captasia? I need 3 minutes to finish here, so assuming this thing will update. All right, the short story is it actually generates a hell of a lot of value, increasing the revenues as predicted significantly for these farms. Come on. Any ideas? No? Okay. I think it's the Captasia. It's trying to catch up and animate. Oh, here we go. Look at that. All right. So these are the numbers in the end, but the point is it shows an increase up to 40%. Very quickly, back to this. And now lessons learned and wrap up in 2 minutes. I talked about this pattern. So let's talk about some of the applications in banking. One of the big things you have to worry about is accessing the data, and we'll talk about that in a second. The other is, can you do stuff in real time? And here we actually used open source, and we worked on a publicly available open source platform called Kamanja. I have the website there. We had the application in Africa, where the first application was alerting people predictively that they're about to exceed their balance in the bank, so act on it. So before you actually exceed and have an overdraft, you get a notice, and you act on it. And the results were amazing. 60% response rate. If you know marketing campaigns, typically 5% would be considered amazing. 80% favorability rating, which is huge for the bank. We use NPS. And there's a couple of other applications that happened right after it because it was enabled by a platform, right? Once you have a platform, you can do a lot of magic. So there's one on influencing customers to move to the digital channel. Lots of good responses. Credit line increases, personalized, also very good uptake and very good responses. We use it in treasury, but I'm going to run out of time. I'm not going to describe it. Treasury in a bank is a place that basically has to collect data from all over the place and tell you what the cash position is anywhere. We use it in FinCrime to basically take the technology and fuse the data and do predictions. And don't have time for risk. So the summary is, real issues you have to face. How do I get to the data? Where is the metadata? Always forgotten. How do I get the data together, right? What's the legal way to join it and so forth? And how do I get the value fast? One of the things I like, you heard Ingo talk about RapidMiner this morning with 20,000 downloads a month. That number always blows my mind because this is not a Candy Crusher game. This is like, if you download it, you must have a real reason and a real need. I'm out of time? Yeah. What this allows you to do, and here's where I get excited about it, is if we are to grab data from this messy infrastructure that I showed you, not only are you a good data scientist, but you have to now become very good at understanding how to run Hadoop, understanding how to run it with classical databases. And the good news here is RapidMiner actually gives you a graphical interface that lets you sort of drag and drop a workflow and then compiles it and runs it on Hadoop. Right? To me, this is huge. This is a big step because it allows you to work on the unstructured and structured world in a very easy way where you don't spend your valuable time wasting that. They also have a really cool feature, the wisdom of the crowd. When I do an analysis session, I do one transformation. This thing actually tells me, the next best or the next most popular transformation is this. And most of the time it's right, which is a pretty amazing feature. So we started out with these questions, and the answers are sadly, what matters in the age of analytics? Where are we today? The new data landscape has disrupted the space. People don't have the talent to understand it. Everybody's confused. And everybody is struggling with the basics, not even doing the advanced stuff. And the real issues are data management and governance. Very boring. You never think about them. Talent, which doesn't exist. And data analytics being recognized as a specialism that needs a lot of energy. So with that, I'm going to take it to questions and leave these lessons learned up here for discussion during the questions. Okay.
Thank you.